In this video, we will learn what a dynamic equilibrium is and investigate how one is established. So what is a dynamic equilibrium? When a reaction occurs, it may go in one direction only to produce products. For example, A reacting to form B. These are irreversible reactions. Or a reaction can move in two directions, both forward and backwards. These are called reversible reactions. Not all reactions have the ability to be reversible. In a reversible reaction, reactants are forming products, and at the same time products are forming reactants. Both A and B will be present together in the same vessel, and we say they are in equilibrium with each other. Reversible reactions can be described as being in either static equilibrium or dynamic equilibrium. In a static equilibrium, there is no movement or exchange between the reactants and products. In other words, the rate or speed of the forward reaction and the backward reaction are both zero. Whereas in a dynamic equilibrium, the rate or speed of the forward reaction and the backward reaction are equal and constant. In other words, the reactants are being converted to products, and products are being converted to reactants at the same speed. And the speed is not changing. However, it is very important to note that the concentrations of the reactants and products may be equal, or they may not be equal. What is most important to remember is that the rate of the forward and reverse reactions are equal. And this has nothing to do with the concentration of the reactants and products. The concentrations of the reactants and products and the rate of forward and backward reactions can be changed if the conditions under which the reaction occurs are changed. We will discuss changing conditions a bit later on. For now, we must consider that a dynamic equilibrium occurs under constant conditions. Let's investigate in what kind of system a dynamic equilibrium occurs. Dynamic equilibrium can be reached in a closed system rather than an open system. What's the difference? The processes or reactions which occur in an open system occur in an open vessel, and in a closed system in a sealed or closed vessel. In an open system, both energy and matter can enter or leave the system. In a closed system, energy can enter or leave, but matter cannot. A reaction which occurs in a test tube, which releases gases to the atmosphere, is an example of an open system. Another example of an open system is water boiling in a pot on the stove with the lid off. Corresponding examples of closed systems would be the same reaction occurring in a test tube but with the stopper in place, or a boiling pot of water with the lid on. Now, in an open system, visible changes might be obvious to an observer. For example, in an open pot, water is free to leave the pot to the surroundings, and over time the level of water will appear to decrease. However, in a closed system, it may look like nothing is happening, even though the forward and backward processes are occurring at the same time. A true equilibrium can be set up in a closed system because matter cannot leave. And if there is constant movement in the forward and backward directions for the process or reaction, we say this equilibrium is dynamic. Now that we know what a dynamic equilibrium is, and that it occurs in a closed system, let's look closely at a reaction that reaches dynamic equilibrium. Let's walk through what happens when a reaction in a closed system begins to the point where it reaches dynamic equilibrium. We'll use the example of nitrogen gas reacting with hydrogen gas to form ammonia. The equation is N2 gas plus 3H2 gas reacting reversibly to give 2NH3 gas. In industry, the synthesis of ammonia gas by this reaction is called the Haber process. we are going to use a sketch graph to understand the formation of this dynamic equilibrium. We are going to plot the rate of the reaction over time. Because we are just going to use sketch graphs, we are not going to use actual values or units, but we are just going to get an understanding of the shape of the curves. Now imagine some nitrogen gas and hydrogen gas are placed together in a closed system, in other words, in a sealed vessel. At time equals 0, there is no product, as the reaction has not yet begun. Under the right conditions, the reaction begins with the forward reaction producing ammonia very quickly. In other words, the forward reaction begins very fast or with a high rate. Because there is no ammonia initially, the rate of the backward reaction is 0. As soon as ammonia forms, some of it will break down to reform the reactants. In other words, a reversible reaction occurs. Although the forward reaction is still occurring quite fast, the rate of the forward reaction decreases slowly over time, as more and more product forms. Oppositely, the rate of the reverse or backward reaction is initially very slow, but over time this reaction occurs faster, as there is more ammonia to decompose back into the reactants. After a certain amount of time, let's call it time equals x, the rates of the forward and reverse reactions are the same. Let's call that rate or speed p. After time x, the forward and backward reactions are in equilibrium. We now know that at dynamic equilibrium, the forward and reverse reactions are both occurring and are occurring at the same speed or rate. And we know that the concentration of the reactants and products are not necessarily the same. Now let's investigate what happens to the concentrations of reactants and product over time by drawing another sketch graph. If we plot concentration versus time, at time equals 0, there is a high concentration of the reactants nitrogen and hydrogen in the vessel. And no product has formed yet. In other words, the concentration of the product ammonia is 0. As the forward reaction begins to make product, so the concentration of the reactants decreases, and the concentration of the product ammonia increases. After some time, let's call it time equals x, the concentrations of the reactants and product remain constant. This is because the reaction is at dynamic equilibrium. Notice, however, that the concentration of the reactants at equilibrium, concentration Q, and the concentration of the product ammonia at equilibrium, concentration S, are not necessarily the same value. In this example, the concentration of the reactants at equilibrium is higher than that of the product. And this is because of the particular set of conditions that this reaction occurred under. The specific conditions of pressure, temperature, or concentration will directly affect the concentration of the reactants and product at equilibrium. Let's clear some space to investigate this a bit further. The first of these three graphs we saw a few moments ago, where the concentration of the reactants at dynamic equilibrium was higher than that of the product ammonia. But there are two other possible scenarios, where the reactants and product have the same concentration at dynamic equilibrium, or where the product ammonia has a higher concentration than that of the reactants nitrogen and hydrogen. If we took the concentration value of the reactants and product in each case, and put them as a ratio of concentration of product divided by concentration of reactants, we'd get the following three results, where the ratio is less than 1, equal to 1, or greater than 1. These ratios give us an indication of the equilibrium position. The equilibrium position can be described as the ratio of the concentration of product to reactants. When the ratio gives a value less than 1, we know that the graph looks like this. When the equilibrium position gives a value of 1, We know that the concentrations of the reactants and product are equal at dynamic equilibrium, and a value greater than 1 indicates that the product concentration at dynamic equilibrium is higher than that of the reactants. Whether we get a graph like the first, second, or third one depends on the equilibrium position, which depends on the conditions under which the reaction occurs. In other words, the pressure, temperature, and concentration directly affect the concentration of the reactants and products at equilibrium. These conditions can cause the equilibrium to shift towards the left, the reactant side of the equation, or towards the right, the product side of the equation. If any of these conditions are changed, the equilibrium position will also be changed, and the concentrations of the reactants and product will change. The details of how these three conditions influence the equilibrium position is a discussion for another video. Other reaction conditions, such as the presence of a catalyst, do not have an effect on the equilibrium position. In other words, they do not influence the concentration of reactants and product at equilibrium. However, a catalyst does affect the rate at which the equilibrium is reached. The presence of a catalyst will cause the equilibrium to be reached faster. Now it's time to practice an equilibrium problem. If a reversible reaction is allowed to reach equilibrium in a closed system, which of the following will be true? A. The concentration of the products will gradually increase. B. Increasing the pressure inside the closed system will not affect equilibrium. C. Increasing the temperature will not affect equilibrium. D. The concentration of the reactants and products will be the same. Or E. The rate of the forward reaction will be the same as the rate of the backward reaction. A reversible reaction is one in which reactants form products and at the same time products are forming reactants. When this occurs in a closed system, which is one in which energy can enter or leave but matter cannot, we say an equilibrium is reached. We can plot the progress of the reaction in terms of rate of reaction versus time from time equals 0. At time equals 0, reactants form products very fast. And at time equals 0, before any products have formed, the backward reaction hasn't yet begun. When some products have formed, some of it will react to reform the reactants, and the rate of the forward reaction begins to decrease. As more product forms, so the rate of the backward reaction increases. From a certain point in the reversible reaction, let's call it time equals x, an equilibrium will occur, and the rate of the forward and backward reactions will be the same. We can see that from time equals x, both the black and green curves have the same y value, in other words, the same rate of reaction. Option E is correct. The rate of the forward reaction will be the same as the rate of the backward reaction. Let's confirm this by having a look at the other answer options. We can do this by doing another sketch graph, this time of concentration versus time. At time equals 0, before the reaction has begun, when there is only reactant in the vessel, the concentration of the reactants is very high, and the concentration of the products is 0. As the reaction begins to proceed, so the concentration of the reactants decreases, as they are converted into products. As more reactants are converted to products, so the concentration of the products increases. However, from time equals x, the concentration of the reactants remains constant, and the concentration of the products remains constant. An equilibrium is formed where the rate of conversion of reactants to products is the same as the rate of conversion of products to reactants. If we look carefully, however, we'll see that the concentration of the reactants and products are not necessarily the same at equilibrium. So we can rule out option D. We can also rule out option A, because the question asks about equilibrium. And at equilibrium, the concentration of the products will not increase but will remain constant. Now, concentration time graphs can look different from the one drawn here. The reactant concentration can be higher than that of the products at equilibrium, as drawn in this graph, or the reactants and products can have the same concentration at equilibrium, or the products can have a higher concentration than the reactants. Taking a ratio of the concentration of the products to reactants will give us a value either less than 1, equal to 1, or greater than 1, depending on the graph. These values, which represent the equilibrium position, depend on the temperature, pressure, or concentration conditions under which the reaction occurs. In other words, temperature, pressure, and concentration do influence equilibrium. So we can rule out the remaining two answer options as they are incorrect. Finally, if a reversible reaction is allowed to reach equilibrium in a closed system, the rate of the forward reaction will be the same as the rate of the backward reaction, and we call this dynamic equilibrium. Now let's summarize everything we have learnt. We learnt that a dynamic equilibrium is an equilibrium in which the forward and backward or reverse reaction rates are equal. We learnt that the concentrations of the reactants and products at dynamic equilibrium are not necessarily equal. And we learnt that a dynamic equilibrium occurs in a closed system. We defined a closed system as being one from which energy can enter or leave, but matter cannot. We also walked through how a dynamic equilibrium occurs from the beginning of a reaction and visualized this using a rate versus time graph. And lastly, we looked at 3 different concentration time graphs, showing 3 different equilibrium positions, and we learned that equilibrium position is influenced by concentration, pressure, and temperature.